Well, we're back. And this is basically the last thing in chapter 14 that we do here. And hopefully it'll won't be too complicated here. Is an important topic, though, namely optimization. Optimization can mean two things, actually. It can mean maximization or minimization. I shouldn't have to tell you that it's sometimes important to do those things. We want our costs to be kept low, or maybe we want to build a box that has the largest possible volume or something like that. Um, and, and that's often an important thing to do in math, right? Um, in fact, you, of course, spent a lot of time doing this uh, back in 191. Okay? And actually, what we're doing here is pretty much just a generalization of the same techniques of almost the same techniques that go on in 191. It's a little bit more complicated, um, but but other than that, it's sort of the same logic. Um, I'm going to focus, I think, exclusively on local extrema. Okay, there's also the question of global extrema, which you guys might remember from 191. But the idea is, again, just to draw kind of the picture. Local extrema are points that are either larger or smaller than points nearby. So in this picture, that would be a local max. All right. Over here we also have a local max. Whereas, say, this one here would be, of course, a local min. Okay? In other words, critical points. So it's the same thing that we're doing. We know that local extrema, local optima must always be critical points, right? So, and this is not going to be any different. That's still going to be true when you do two dimensions, but that's what we're going to focus on. A global, in this particular case, the global min would say be down here, something like that, right? Because it's actually less than everywhere else. It doesn't have to be a local min, but again, I just want to focus on the local stuff because that's really where the calculus comes in here anyway, right? So just real quickly, let me remind you of the one-dimensional case, right? So, and you should remember this. So if a point X is a local extremum, the extrema means kind of like optimum. It could be either the largest or the smallest. This works for both. In fact, if you're doing a maximization, all you got to do is stick a minus sign and you can turn it into a minimization. Anyway, then, if X is a local extremum, then we know it has to be a critical point. Okay, in other words, the derivative of that point must be 0. Now, I'll mention in passing here, without spending too much time on it, that the converse is not true, right? So if it's an extremum, then it must be a critical point. But just knowing it's a critical point, just because we would know this, doesn't mean it's necessarily an extremum. All right? And I guess I will give a quick example of this, right? So the function, say y is x cubed, looks something like this. That guy actually is a critical point because the derivative there is 0. However, you can see it's not an extreme. Okay, once again, So these same sorts of things can happen in 2 dimensions as well. Anyway, there's a couple things that you do to find this out. There's a so-called first derivative test to find out, and all you do there, of course, is check and see if indeed that's the case. If it's not, you can forget it because it can't be an extremum. But the first thing you do is the first derivative test. So we're checking to see if x is a local extremum. The first thing you do is take the derivative, evaluate it, and see if it's 0. There's other problems, of course, too. You could do the other way if you're looking for extremum, but let's just talk about it this way, okay? So if I have an x and I want to know, the first thing I do is check its derivative and see if it's equal to 0. Then, assuming it is, the next question turns out to be, well, is it a minimum, or is it a maximum, or what? And so that brings us to the second derivative test. Okay, and it goes this way. And so let's assume this is true. So we're at a critical point. If it turns out that the second derivative evaluated at that same point turns out to be positive, then you can assume that then you know it's going to be a local min and not a max. And that's really all there is to it. I'm not going to belabor this because you've seen this. If the same thing happened but it turned to be negative, then that would turn out to be a local max. And the last thing we have to worry about is, of course, it's always possible that it could be 0. And if this is the case, then the test fails. You can actually go on, and if the test fails, here you can go on to the third derivative test, fourth derivative test. It all depends on the first one that's not 0, but let's not worry about that too much here. Let's just go and do that. So anyway, here's how you do it in 1 dimension. Well, it works out pretty much the same way in 2 dimensions. All right? So now we have a function, which of course is now 2-dimensional. Right, that goes there. And now to check for critical points of 1 dimension, you always look at the derivative. And so to check for critical points in 2 dimensions, you look at the gradient. It's pretty much the same logic, right? I mean, it's a little bit differently that you're computing and all that stuff, but this is what you look at. Now, anyway, it still all works the same way in this sense that a pair of coordinates x, y will be a critical point if the gradient is now the 0 vector. Okay, so it's the same thing, you're just doing it twice. Again, there's none of those deals where 2-dimensional calculus is really just 1-dimensional calculus done twice. Okay, and so that's what you do to look for a critical point, and then basically that's the 2-dimensional version of the first derivative test. Okay, now the second derivative test is where it gets a little more complicated. Okay, and so anyway, the first thing you got to do, you either set variable to 0 to find x, y, or if you had an x, y, you stick it and you find out, whether it's a critical point or not. But same kind of thing works out. That's what you're looking for. Okay. Once again, then let's assume that we have a 2-dimensional critical point. And basically all I got to show you is the second derivative test, and that's pretty much all there is to this. Let me go ahead and redo this. Now, when you're talking about the second derivative test and when there's two dimensions, you can see right away there's an ambiguity there. Because now the second derivative test in one dimension, you just find the second derivative, and that's all there is to it. Now, we need something a little bit more complicated. Let's just do this way. All right. And many of you know that when you put, and we've talked about it a little bit, I think, in here, but when you line up numbers like this as a square array rather than a vector, it turns out to be something called a matrix. And this particular matrix constructed in this way is called the Hessian matrix. It's not important, but that's what they call it. But anyway, you can see what the elements are. There's the second partial derivative with respect to x. The second partial derivative with respect to y, and those are the diagonal elements. And then over here, we have the cross derivatives, fxy, which is the same as fyx, otherwise none of this makes sense anyway. All right, so this is the thing that we need to look at. I need to check some notation. Give me half a second, I'll be right back. All right. When you have matrices, something that's very important to do, an important quantity that shows up all the time, is called the determinant. And the determinant of the Hessian is that. But we saw this when we did the cross product, didn't we? That's where this, because it's simply that product minus that product. Okay, and so these are the things that we're looking at again to find out about whether the point xy might be a local min, whether it might be a local max, or neither. Anyway, sorry, I gotta check this again. My memory is going. Yeah, okay. And so here's the way it goes. So if this determinant at that, because remember, at a point, if this determinant happens to be positive, and also the second derivative has to be positive, and I forgot this again, darn it. Sorry. Then it turns out that it is a local max. And you can probably see where I'm going with this now. If D, well, maybe not. There's a couple things to look at. If D is positive, and this fxx turned out to be negative, but you know what? I got those backwards. I should have known better. That's the minimum, that's the maximum. Local min or local max. Okay? And that's what we get there. And then now you can also think, well, what's the last thing that we're leaving out here? Well, There's always the possibility that this determinant of this Hessian could be 0. And then, of course, you might guess that the test fails. I'll just mention quickly here that I say XX is, I chose this one, but you could equally well use that one. Okay, and so anyway, once again, you'll do some homeworks on this and get to play with it. It's not hard to do, though. It's generally not very hard to do as long as the derivatives and the function that you're dealing with aren't too bad, but you can really see again that it works just about the same way. I think that's all I've got to say. Yep. And that's it. So that's the way it works. So you find your critical points, and then you have to do the two-dimensional version of the second derivative test. All right? Well, once again, this has been a pretty long video already, and you guys are going to do your own homeworks anyway. We could look at some of this sometime in the future, but I'm going to go ahead and shut her down.